So our next speaker is Upala, and she's going to tell us about dark energy according to James Webb observations.
So first of all, thank you to the organizers for giving me this opportunity to present my work here, and thank you all for attending my talk. In this presentation, I will talk about two of my works. Here are the references where me and my collaborators have studied different dark energy models in the light of the early JWST observation, that is in the light of the high redshift massive galaxy tensions reported by the James Webb Space Telescope. So before going to the detail of my presentation, I would like to thank my wonderful collaborators Sunny Bagnodzi, Nicola Menzi, Anjanananda Sen and Shahnawaz Adil. I have learned a lot of things from them. So ΛCDM is the standard model of the universe, where this lambda is the cosmological constant, which is the candidate for the late time cosmic acceleration or the dark energy, and CDM is the cold dark matter, which is the component for this dark matter component. So all we know that ΛCDM is very well accepted and very popular, but still it now faces major cosmic tensions, and those cosmic tensions were very beautifully described in this conference. So I am not going into the detail of it. So maybe all these cosmic tensions are indicating that ΛCDM is not the ultimate model of our universe, and maybe physics, we need to explore new physics which are beyond this ΛCDM scenario. In this presentation, I will particularly focus to this tension, which is the high redshift massive galaxy tensions reported by the James Webb Space Telescope very recently. So what is that? They have reported very massive galaxies. Their masses are greater than 10 to the power 10 solar masses at very high redshift range between 7 to 10, and surprisingly a very high population of such massive galaxies at that redshift. But according to ΛCDM, such massive galaxies cannot be formed at that early time. So ΛCDM fails to explain this very recent observation of JWST. We have tried to see whether any alternative models of dark energy can explain this high redshift massive galaxy tension. So in our work, we have considered a combined dark energy sector, where one of the component have this evolving equation of state of dark energy, where we considered the CPL parameterization for it, and the other component has a constant equation of state, and for that we have considered this negative cosmological constant scenario from the inspiration of string theory, because it appears ubiquitously in the string theoretical scenarios. So we first analyze the results and see if we do not consider such cosmological constant in our scenario, then what will be the results if we only consider this evolving dark energy equation of state. And then on the top of that, we have considered this negative cosmological constant and have observed whether this affect the results, and if yes, how much it modifies the result, and if that could be probed by these high redshift observations. So our total omega d should be around 0.7. So this omega lambda plus this omega x for this dynamical component is equal to the 0.7. So this is the Hubble rate for our model, and with the help of this we have calculated the density perturbations and calculate the growth factor. So in our case, we have considered this scenario. First, for the comparison, we calculate the ΛCDM scenario, and then we take a quintessence-like dark energy with a constant equation of state, phantom-like dark energy with constant equation of state, and then dark energy which is quintessence-like in past and phantom in present, or quintessence-like in present, phantom in past, and all these combinations. Then we consider a non-zero negative cosmological constant in the scenario and see whether it affects our result or not. So then these are the growth factor we have computed for different parameter combinations as I described. So, from these are plots, this dz versus z for two range of the redshift. One is the lower redshift from 0 to 2 and one is the higher redshift from 7 to 12. So, from these two plots we can we can notice two important things. First is that these solid lines are corresponding to the cases where omega lambda is 0 and the corresponding dotted lines are the cases where we have assumed there exists a negative cosmological constant. So, we have seen that if dark energy behavior gives larger growth factor than the lambda CDM, then the existence of the negative cosmological constant in the scenario gives much higher growth factor. Similarly, the opposite ones. So, the presence of a negative cosmological constant is indirectly increasing the effect of the dynamical component of the dark energy. And the other thing which is we found very interesting is that this deviation of growth factors of different models increases with the redshift range z. That is the deviations between different models between this low redshift range is smaller than the deviation of these different models in this high redshift range. Although dark energy is a component, we know the effect of dark energy appears in the late time universe, and late time cosmic probes are very important to understand this behavior of dark energy. But from here we can reinforce that even this high redshift massive galaxy observations could be a very good probe to understand the different behaviors of dark energy scenarios. So, from here we calculate the halo mass density, and from that we calculate the cumulative stellar mass density, where this epsilon is the efficiency of converting the gas into stars and F is the cosmic baryon fraction. Then we calculate the rho star, and yes, here we have plotted the rho star versus m star for our different scenarios, and it is for different redshift z. Here also we can see that the deviation between different models increases with the redshift value. These 6 points are the corresponding 6 massive galaxies found by Labe and his collaborators, which cannot be explained by this lambda CDM scenario, but we see that if we consider a dynamical approach of dark energy and on the top of that a negative cosmological constant, then it can accelerate the growth of structure, and it is more favorable in the context of this JWST observational results. But of course, these are an exploratory analysis. To comment more in a more concrete way, we have to analyze our model with cosmological data sets, and for that we consider first these two data sets. First we have considered this thing where there are 6 massive galaxies at the redshift range 7 to 10 found by Labe and his collaborators by doing a photometric analysis of the JWST Sears program. We compare our model with this data and found constraints on the model parameters. Then we compare our model with this data where 3 massive galaxies whose masses are greater than 10 to the power 11 solar masses at redshift range 7 to 5 found at redshift range between this 5 to 6. So, these 3 massive galaxies were found by Xiao and his collaborators by spectroscopically analyzing this JWST fresco survey. So, we do the MCMC analysis and found this redshift region which is allowed by the data I have discussed. So, it appears that dark energy sector featuring a dynamical component with CPL and a negative cosmological constant on top of it have potential to explain these high redshift massive galaxies found by JWST. And also we have compared our model by analyzing it with standard probes like CMB, BO and supernova. These are these black region and found that yes, it is also highly complementary to this standard cosmological scenario. This is the result for JWST CS survey and this is for FRESCO survey, and we have obtained these similar conclusions, which is interesting. To conclude that we have tried to explain the high Z galaxies observed by JWST, which are in tension with the ΛCDM scenario. For that we have considered a dark energy sector which have a dynamical component and a negative cosmological constant on top of it, and we have found that yes, this type of model have potential to explain such high massive galaxies observed by this JWST. And also we have found that this allowed region is highly complementary to the standard cosmological probes like CMB, and supernova. We have also reinforces and strengthened the case that these high Z data sets of galaxy clusters can be a good probe to test these dark energy models. In future it would be interesting to constrain this model from other results like gravitational lensing, and also it would be interesting to find a theoretical origin of such a well motivated phenomenological model. So yes, thank you for your attention. I think.
Thank you, Upala. We have questions over there?
Okay, thank you for the very nice talk. I have a question about the stellar masses and what's the kind of accuracy of the measurements, how much can we trust them, and also the stellar mass to halo mass relation is very important for what you're doing, right? Because ΛCDM doesn't really directly predict the stellar masses, only halo masses. So in principle, one solution could be to change that relation. Have you kind of looked at that or thought about it?
No, we haven't thought about that. What I can comment is that the stellar masses they obtained is around 10 to the power 10 solar masses, and I think those are not yet spectroscopically verified photometric results. But yes, what you are talking about to see that in that scenario, no, we haven't thought about that yet. Yes, but thank you for the suggestion. We can think and talk with it. Yes, thank you, thank you.
Thank you, very nice, interesting idea. Although I would say the following. So let's say that we take seriously the JSW high Z galaxies as a challenge for ΛCDM. Yeah. But your solution also might have a problem with that, because in a sense we understand there is a cosmic variance, halo to halo, galaxy to galaxy scatter, and in ΛCDM you can say maybe that you see extreme outliers in the halo mass to slow mass population or very early galaxies, because vacua model only predicts mean. Now you offer a solution that you change the growth rate at the high redshift. Yeah. So now what you predict as a mean will be this galaxy that might be outlier in ΛCDM. So wouldn't naively expecting that your theory predicts that JWST telescope should not observe much more of these high Z galaxies than we actually observe? Wouldn't you have an overabundance of this high Z galaxy problem? Because you move to the mean, right? Your theory predicts there should be more of this. Yes. In ΛCDM, we can always say, okay, we only see the outliers at the moment. So background model of cosmology doesn't predict galaxy formation. It's extra theory. So we understand there's a cosmic variance, there are many scatters. So even if you predict the mean halo mass function or stellar mass function in ΛCDM high redshift, there is a distribution around this, and there will be outliers. So in ЛCDM, one of the explanations provided so far is a working hypothesis for the observations that these high Z galaxies that James Webb Telescope sees is just basically outliers. They are very uncommon, but just because we see them because they are already outliers, you see at this redshift. Now you modify the growth rate. Now you actually predict there should be more of them because now your mean prediction is higher than ΛCDM prediction and higher redshift. So wouldn't this actually be translated into many more suggested observations of these high Z galaxies by James Webb?
It's an interesting point, right. But yeah, we haven't thought about it, and I think we have found this as rho star is much more than what is predicted by ΛCDM, so that problem can arise. But we have constrained our parameter space with the already existing data set. So within that limit, I think this rho star is not that much greater than the ΛCDM, which predicts many numbers of that high massive galaxies that you are suggesting that I think.
To be fair, we need to wait for more observation.
Yes, right, that's true. That's
okay,
true.
thank you.
Thank you.
You consider the cosmological constant is smaller than 0.
Yes,
And then,
right.
I don't think this is a good model because current constraints do not support it, and more importantly, you use the relation omega lambda plus omega x equals 0.7. I've checked your model. I remember 1 year ago, because the dark energy and this negative cosmological constant is highly degenerate. I checked the constraint, so I don't think it is a good model. And another point is, if one want to explain this JWST anomaly, one must use the first step. One should use one should constrain his model with cosmological constant, cosmological data, and using in light of these constraints, I think one can check whether it's consistent with the JWST observations. And then I wrote a paper 1 year ago. I found it's very hard to explain this JWST observations with any cosmological model. So I don't agree. So I think it's because it's just this anomaly comes from astrophysical origin. So I don't think it's a cosmological origin.
Okay. Okay, thank you for your comment, but I would like to add one line here, that this type of model can be assumed to be formed with a scalar field model which behaves like a quintessence model, but its minima is a negative minima. So this type of model is explained in this way in the literature, where there is a dynamical component and a negative cosmological constant.
Let's thank Upala again.